If I were to give a one-sentence definition of Bayesian data analysis, that definition would sound like this. Bayesian data analysis is a way of statistical modeling that treats all the unknowns in our analysis as random variables. So what do I mean by the unknowns here, and what does it mean to treat them as random variables? The unknowns in this context can include a variety of different things. These are the quantities and qualities that are in some way important for our analysis, but at the same time we cannot get them directly with the data, they are not part of the data, and we choose not to fix them at specific known values. First and foremost, these unknowns include the parameters of the models that we are trying to estimate. Let's say, for the sake of an example, that we are looking at a regression model. We are trying to relate the values of the dependent variable with the values of the independent variables through some sort of a linear expression. The values of the dependent variable and the independent variables that we have in the data are the knowns in this analysis. The regression coefficients, the coefficients in that linear expression, are the unknowns. If, for example, instead of looking at a regression analysis, we are looking at a model in which we are trying to connect the observed characteristics of our observations with the unobserved latent characteristics of our observations. We are going to know the values of the observed characteristics for the observations in our dataset. However, the values of the latent variables are going to be unknown to us. The unknowns do not have to include only the parameters of the models. If, for example, we have missing data, the missing values of the variables in the sample that we have on hand are going to be the unknowns. Likewise, if we want to make predictions about the values of the variables in the future observations, in the observations that we have not observed yet, then those are also going to be unknowns. We can also treat as the unknowns the parameters of the distributions that we use in our models, and even the types of the distribution that we choose to use in our analysis. Now to the second question. So what does it mean to treat the unknowns as random variables? To treat the unknowns as random variables means to assign probabilities to all the values that these unknowns can take. This can be done in a number of different ways. First of all, we can list all the possible values of our unknowns and assign probabilities to each of those values. As shown here on the slide, we can say that the variable lambda takes the value of 1 with the probability of 1/2, it takes the value of 2 with the probability of 1/3, and it takes the value of 3 with the probability of 1/6. The variable lambda will take any value other than 1 to 3 with the probability of 0. Another way of specifying or assigning probabilities to the values of our unknowns is by describing them in terms of the standard theoretical distributions. We can say that a quantity beta follows a normal distribution with the mean equal to such and such value and the standard deviation equal to such and such value. If we are not satisfied with the selection of the theoretical distributions, we can come up with our own probability function and describe the distribution of our variables of interest, of our random variables, using that probability function. In any case, by assigning probabilities to the values, the possible values of our quantities, we are putting on the paper our beliefs about the most likely values of those quantities, and we are also putting on the paper the amount of uncertainty that we have about those values. Once we put those beliefs on the paper, or formulated them in the memory of our computers, we can do all sorts of operations directly with these beliefs. We can use the information that we have in the dataset to update these beliefs and to come up with more reasonable beliefs about our unknowns. We can also use those probabilities, use those beliefs to formulate the beliefs about the related quantities of interest and assess how consistent our beliefs are across different related quantities. And this is where the power of the Bayesian analysis comes from our ability to manipulate the beliefs, our beliefs about the unknowns in our analysis directly. The exact workflow of Bayesian data analysis is going to depend on the models that we are trying to build and the exact goals that we are trying to pursue. Let's take a look at the Bayesian data analysis workflow in case we are trying to perform a regression analysis. Such an analysis is going to start with a model of data generation with the unknown parameters and some sort of initial probability distribution over these unknowns, over these parameters. Our beliefs about the unknowns in our data generation process before we observe the data are going to be called the priors. Once we have the data, and once we incorporate the data into our analysis, we can update our beliefs and arrive at the updated probability distribution over these unknowns, over these parameters. And this distribution is going to be called the posterior. The posterior distribution is a major product of the Bayesian data analysis. Once you have arrived at the posterior distribution that you are satisfied is consistent with the data and with your prior beliefs, you're half done with this analysis. Once you have the posterior, you can use that posterior to generate point estimates for your parameters. You can go ahead and generate all sorts of quantities of interest, the measures of the uncertainty around them, generate the predictions for the future values of your dependent variables. And if you wish to do so, you can use your posterior distributions as inputs for further analysis, for further updates of the beliefs.